Thanks. Hello. Today I will present some work that has been developed in my lab in Université Claude Bernard Lyon. The aim of this work is to produce low-cost flexible device, mainly micro and microfilters and micromixers, using unconventional technology. What that means, we will use, instead of silicon technology, we will use soft lithography. Well, the outline of my talk, first I will start with motivation. I will explain why we would like to do that. And I will present the manufacturing of micromixers and microfilters. After that, how to functionalize the device, because we need to make sealing between microfluidics and some substrates, mainly based on polymers, different polymers. And I will show you some applications, and finally I will conclude. Well, here, when we start to do these devices, we start using silicon technology. And silicon technology means that we need to have cleaner room and so on. And for that, we use different techniques for making basically this bonding: direct thermal, solvent bonding, laser welding, epoxy, and PDMS. The advantage, high zinc bonding. However, they have some drawback, because we need cleaner room, we need anodic bonding to do that, high potential, and so on. And now we are working, and the most important, it's not flexible devices. And sometimes we need some flexible devices. The aim of our work is to produce these devices that will be flexible, fully based on polymers, and avoiding all this drawback, because sometimes we need to use strong solvent that can damage the structures, difficulty to remove completely the epoxy after covering these devices with epoxy. And our idea to use PDMS microstructures, and on the other hand, substrate based on pen or PET, whatever, using chemical treatment in order to do this bonding. Well, the objective, first of all, we will produce stamp bearing microfilter or micromixers. And after that, we will functionalize the substrate, and after that, we will seal it together just by slow pressure, and after that, we will see some applications. The most important here, the critical part, is the first one, it's the aspect ratio, and the second one, how to do well the functionalization. First of all, to produce the stamp, because we need the stamp, the master based on silicon technology. This is easy. And the process is the following, the standard way. We grow the silicon oxide, we put here the solvents, and we expose to the mask to UV, and after that we do development of resin, we etch the first layer, and after that we do reactive ion etching in order to create our structure, channels, loops, and whatever, pillars, and so on. And after that we remove the silicon oxide. Well, this is the structure that has been developed in collaboration with our colleague from CNM, from Spin via Terra. We can see clearly here, this is silicon in which we have several loops. Well, this was optimized previously because we need minor loops in order to achieve mixing. And the aspect ratio, it was very critical in this case, because if not, we can have some collapse and so on. Here we have some information regarding the channels between 200 at the beginning here, input. Why we have two inputs? Because we would like, for instance, to inject blood and anticoagulants and to make mixing, and after that to analyze by optically or whatever if we have antibodies labeled with fluorescence with antigen. Okay, after that we need to produce our master. Our master is based on polymers, PDMS in our case. For that, we need to use soft lithography. What that means? First of all, we have the silicon master that we need to functionalize previously, because after that we will put here the PDMS and we will put it in the oven during 30 minutes, and we need to peel off this. Without this, we will damage our structures and will not be useful to use it, because we can have some leakage and so on. After that, we have our PDMS masters that we will use it as a substrate. We can see here clearly this is the stamp silicon master, and after the replica, and after again the replica negative, because we would like to have the negative, because we would like to inject and to make the mixing. Well, now we have the structure microfluidic systems, and we need to close the channels because we need to inject. For that, we start using these silent groups, and we do activation with plasma, and we do the functionalization with the silent. And after that, this part, it's basically, we use PET pen and polyamide, and after that, we do the oxygen plasma in order to activate PDMS, and after that, by simple, by simple contact, we have a good bonding. Here, I show you all this substrate has been tested, and we test to glass because it was the reference for us in order to see if we have some leakage and so on. Well, this is the prototype, as we can see here. These are the loops here, and this is PET as a substrate, PDMS, and after that we start to inject two kinds of liquid in order to see if we are able to mix inside the loops. In fact, we start here, and not only that, we apply pressure here in different regions in order to see if we can block the channels or loops or whatever, and we can see after that we have a nice mixing at the end. That means our polymer, we have not leakage, and the saline part, it's well done. However, it's critical, this part, because we must know at which page, if not, we can have some polymerization of silane, and we will not have some self-assembled monolayer. And this is critical for this kind of functionalization. Well, this it was first, and here we can see we inject iron and we inject resin, both. We can see at the beginning in each compartment we have two kinds of things, and after time we start to mix all together. It takes less than 2 minutes to have something that can be mixed. I can show you the video. Maybe this one. You can see clearly it's quick, and it's enough time for us for such analysis, because we are doing some analysis using blood with the disease health filer to study the interaction between antibody and cytokine, and it was working very well. Let's go back to our presentation. Well, and after that, we start to increase the degree of difficulty. What that means, we start to inject other things, like magnetic particles labeled with fluorescence in order to see if we are able to mix all together. And we can see clearly here at the beginning and at the end, and we can see we fill all these loops during less than 5 minutes. Let's talk about the second part, filter. We are able to select or to just filter in, for instance, if I have blood and I would like to select some specific protein that at the end I can analyze by electrochemical techniques. Yes, here I present again the devices that has been fabricated in CNM with different structures, with different size. You can see here pillars at the beginning, and the distance decrease in time. You can see at the beginning, and we have rectangular and cylinder, and we have another kind of lines. All these structures has been analyzed with blood and with nanoparticles. Again, the same process. We use soft lithography. We make the replica on our device. Sometimes we have some difficulty because you can see here the pillars are not very well, but the most of devices are working very well because when we inject, they come up. I don't know how to explain this, because at the beginning we have some structure, but when we inject some solvents or liquid medium, they start to work very well. Well, to test our microfilters, we use different size of nanoparticles here, magnetic particles, and we can see here for the first part here we have the microfilters blended on and PET and PET, and we can see that we can select, depending of the size of the nanoparticle that we have injected, we can select at the end what we would like, and it depends on the size between pillars. Because, for instance, here we are using micro, but we are developing nano pillars using vinyl. And we can see at the beginning here, just to compare, it's here. However, it moves. That means at the end, we will only have this kind of particle to analyze with electrochemistry. Well, now the final idea of this is to combine both. We are able to do micromixer, we are able to do microfilters. We can merge together, and the idea is to merge both and to analyze with the impact in field of biomedical, because we have our colleagues that are working in health filer, and they would like to select at the end some cytokine, because the most important difficulty when they are using electrochemical measurements, in fact, blood is strong medium and they have proteins that can mask the response and so on. The idea here is to mix blood with anticoagulant, to make a filtering, and to have only this solid protein, or I don't know the proper name, and to analyze after with electrochemical, avoiding all this process of adsorption on top of our electrochemical device. And we start with something easier. We connect both, we inject here, and we can see clearly in our image that we can mix these both that. Well, now what we are doing, we start to integrate both devices, because it was the first prototype, and we showed that we are able to produce it. Now we are integrating microfilter, micromixer with lab-on-chip, with the electrochemical device at the end. All this based on soft lithography with micro-contact printing. We don't need clean room. We don't need etching. All it's done by micro-contact printing to produce electrode, and soft lithography to produce microfluidic and microfilters. As a conclusion, we can say that we are able to produce with simple way devices that are fully flexible and can be used for biomedical or for other analysis. And the main challenge here is to know the aspect ratio in order to avoid some collapse in microchannels or in filtering. And we tested with liquid medium, and we tested with nanoparticle. It works. And now our idea is to merge all together to produce a lab-on-chip in order to do all these steps meantime. Thank you for your attention.